Okay, good morning, ladies and gentlemen. The topic of today's presentation is a novel magnetic catalytic CMOS gas sensor with ultra low power consumption. The presentation will take about 10 to 12 minutes. I'll be glad to take any question after my presentation. Let's start with the first topic. The directory outlined here is abstract motivation, principle, experimental flow, component architecture, and result. The first topic here is abstract, which briefly introduces the CMOS MEMS gas sensor. The conventional prototype gas sensors are mainly divided into three forms: catalytic combustion type, absorption type, and electrochemical types. The chemical reaction function were marked below. First of all, we will coating tin oxide on the surface of the electrodes. Tin oxide is the most common metal oxide used in gas sensor, which includes the high sensitive and fast response time. When the carbon monoxide injects into the chamber, it will fill the oxygen vacancy of the tin oxide and releasing carbon monoxide and free electrons. The resistance value decreasing with the increase of the free electron. Why is important with our proposed sensors? The conventional chemical sensors usually improve the sensitivity by heater to maintain the high operational temperature. Chemical sensor tin oxide can reach high resolution of gas concentration with heating power to maintain the reaction rate. Our proposed sensor abandons heater through the ferromagnetic field to enhance the sensitivity to achieve the same effect as the thermal catalysis. And nowadays, we found there are still some issues that seriously affect the chemical sensors, such as the high power consumption and the aging of the sensing material. The second topic for the motivation is to improve the disadvantage from conventional gas sensor to achieve low power consumption. Conventional semiconductor gas sensor use the heater to maintain the high temperature state. The resistance change with gas concentration into a certain relationship as a detection principle with the semiconductor metal oxide and combustible gas contacts. How can we enhance the reliability and low down the power supply and promote the detecting sensitive at the same time? The disadvantage for the conventional thermal catalysis gas sensor will cause the premature aging of the chemical material, high power consumption, and restriction on the CMOS process. High temperature around 250 to 300 degrees will seriously damage the metal wire. Our proposed sensor takes advantage of tin oxide doped with magnetic through the Shu-Jung method to prepare the sensing material, and applying on the sensor structure by magnetic catalysis, we can enhance the sensitivity. And how do we think of magnetic catalysis can replace the thermal catalysis? In fact, the idea is very intuitive. Recently, there are some papers because the characteristic of doping magnetite in tin oxide can increase the porosity. To do so can reduce the rupture due to the high temperatures too. Based on the transition state, thermodynamics shows the reaction rate proportional to exponential of Gibbs free energy, and can express as the function below the statistical thermodynamics. Gibbs free energy defines a combined enthalpy-entropy function that determines spontaneity of a process or the amount of energy that is left after a reaction takes place. It is well known that magnetic field and chemical reaction rate has a close relationship. Magnetic catalysis will affect the rate of chemical reaction, which is the original concept of our research work. Therefore, from the equation 1 and 2, one can notice that the chemical reaction rate is affected significantly by the external magnetic field. Next, the experimental flow is here. First of all, we will prepare the sensing material. Second, coating on the PCB, and we can measure it by multimeter. In this situation, there are several pH conditions under test to sampling the sensitive one. Finally, coating the pH 9 material on the actual chip and send it to dry. The component architecture here by use of the minor spacing between electrodes applying to gas detection. The photograph here shows us the actual sensing structure before coating, after coating, and the metal layers under the electrodes. From the result of our research, the best pH condition of tin oxide is pH 9, and the sensitivity will increase with the magnetic field. So, in conclusion, the magnetic catalysis in our research can enhance the sensitivity and even better than thermal catalysis. Thank you very much.